So hello everyone, welcome to our second lecture series of the network inequality. Today we present the work of Jordan Kemp. He's a PhD candidate at the University of Chicago in the Department of Physics, and he's working on the model of growth and of dynamic of like social systems and things like that. And under the supervision of Louis Bettencourt. And today he will show us his work on cooperation and inequality in information threading, models of growth. So I think, Jordan, the floor is yours.
Thank you for having me. I'm very excited to be giving an international Zoom call here. I'm a PhD student at UChicago, as was mentioned, and I work in the Urban Sciences Lab. And so we'll get into what that means in a sec. But today, I'll be talking about what I've been working on for the last couple of years in deriving these novel models of cooperation and wealth dynamics and inequality using information theoretic agents. And so we'll also get into what that means in a bit too. So to start us off, I want to talk a bit about, what is required to really create a theory of social organization. And I'm not implying that this is the work that I do, but it's a really good question to ponder as we enter this talk. And the really key thing here is that each different level of social organization, there are unique challenges. So we're most familiar with the challenges at our own personal level, the choices of how to spend our time and our money on a daily basis. How do we form relationships through our social networks? How do we manage our incomes? And then as we start to scale up into families, communities, cities, et cetera, these needs get more complex and are based a lot more on interactions, up to the point of the global needs, such as cooperation and general resource management. And so the sciences generally have tried to come up with indicators of well-being at each of these different levels. So for example, at the individual level, we have education and health. At the global level, we have things like GDP to measure productivity and Gini to measure inequality. But there's not currently a lot of good tools to relate, these quantities across these different scales, with the special caveat that there's often bijective and really complex interactions between these different levels of scale. And so over the last, for as long as science has been around, people have been trying to tackle these problems, historically using the social sciences, such as psychology and sociology. And more recently, scientists have been attempting more quantitative treatments through biophysics and techniques from ecology. And so generally, urban science wants to unite these two perspectives, from the social sciences and from the biological sciences, and working from essentially the ground up and trying to come up with models at scale. And these scaling models are really what have been the most fruitful products of urban science over the last couple of decades. And the idea of a scaling model is trying to understand how do quantities, particularly in cities, increase as the size of the city increases. And so these models typically start from some really simple budgeting condition that in our daily lives, we are essentially tasked with balancing the incomes that we receive from positive interactions in our world and the costs that we expend. And so that budgeting condition takes this really simple form here, where Y is those incomes and C are those costs over some trajectory that we take as individuals. The beauty of urban scaling theory is that we don't really need to worry about those details, because we can simply, I say simply, but that's where all the new problems lie, but we can average over the trajectories of individuals and the interactions they make to start to quantify these behaviors. And so this plot here demonstrates a lot of the triumphs of urban scaling over the last few years, where they've been able to prove and compute the scaling coefficients of a lot of these different urban quantities, such as crime rates, GDP, income, et cetera. But probing more into this problem of how do we understand this budgeting condition is really where my work has really been taking off from over these last few years. And so this leads to the general question of my talk, is how do these aggregate quantities, particularly of growth and cooperation, emerge from complex agent behavior in uncertain environments. And so I say uncertain because, of course, the dynamics of our world are much too complicated to try to come up with closed form or deterministic solutions. So we take a cue from the biophysics community and as well as the econophysics and think of our world as being really statistical. And so what that means is that the challenge is for agents, the agents must find a way to survive generally in these uncertain environments that particularly reward intelligent decisions on average. And so by environment, I mean a combination of the social, so through their social networks, the natural environment, you think about like where people get resources, as well as the built environment, such as cities. And so we set up our research as tackling and trying to understand this relationship between these intelligent agents and essentially the world around them that rewards them. And the general upshot of my research is that agents who allocate their resources, such as their time and their money and their energy, they grow proportional to the information they have about their environment. And from these quantities of information, we can start to understand how does learning take place and how does cooperation emerge. And so for the rest of the talk, we're going to be considering this complex environment in a very simple case, one that's just essentially a black box that has some statistical behavior that the agent can observe. And so what I mean by information, I mean in the statistical sense. So if you imagine an agent that is receiving a lot of signals from their environment, investing in a lot of events from the environment, these two quantities, signals and events, as statistical quantities can have some distributions that relate to one another. And so usually the other way that we consider relationships between two quantities are correlations or covariances. And so before we get into the talk, I just want to illustrate how these two quantities actually differ in practice. So to illustrate this, I've mocked up some data here for us to look at. Some data on just a generic X and Y plot. So there's no actual meaning to this yet. But as you can see in each of these different plots, we have a different best fit mean. So a different calculated correlation value, if you will. So the main idea of mutual information is that it reduces the uncertainty of a quantity when you condition it on a second quantity. So for example, if we're trying to understand what is the distribution of this Y variable that we're observing, when we condition it on X, we see that this uncertainty of Y, that in this case spans the whole range defined, when we pick a single value of X, gets reduced pretty dramatically. And so in this sense, we would say that this data has some high information content, or there's a lot of information that connects X and Y. But this also, of course, has high correlation. Now we can look at another case of data such as this here, where now, depending on which X you pick, there's slightly less information gained. The correlation is also a little less strong. So we'd say, in both cases, there's a moderate correlation or moderate information between the two variables. But in this final case, you can see that there's no correlation, but we do have information. So of course, a smarter person would, fit this to a higher degree polynomial. But in terms of determining like a correlation between these two values, there isn't. However, there is a lot of information. So in this sense, information is a very general way of looking at how two data relate to each other, one in which you consider the relationship between their distributions rather than a relationship between their outcomes. And so with that, we'll get back to the actual content of the talk. So in this talk, I will first derive this theory of agent behavior and demonstrate how it relates to common models of wealth dynamics and wealth inequality. And I'll provide a very simple illustrative example that helps us bridge that gap. And then we'll show how learning becomes a mechanism in certain cases of reducing inequality across the population. And then second, I'll show how information gives us a lot of power in deriving special relationships such as benefits to cooperation. And then the talk will be over. So first, let's start with adaptive behavior in noisy environments. So I said before that these agents exist in an environment that reward proper predictions, and this is a pretty realistic assumption, right? If you if you're a forager and you know where to find berries, you'll be rewarded with some food, right? And we take this to in the very general sense, where if an agent can properly predict where that an event will occur, they will receive some reward for that event that is inversely proportional to the likelihood of that event happening. Agents all receive private signals from their environment that inform how they allocate their resources towards that event. And so that private signal is sampled in the form of some S variable. And then there's this matrix of resource allocation on all of the events that is informed by that S. And so when you have a setup like this, Kelly in the 50s proved that the optimal allocation strategy is one that matches some conditional probability of those two variables. Kelly says that the optimal is really when this X matches that P. We'll talk a little bit about what that means later. But for now, we'll just say that the agent does the best that they can in a sense similar to some like bounded rational choice, that they're allocating their resources proportional to this model. And so to see how this is, to illustrate how this works, every time step of this interaction proceeds as follows. The agent receives some signal from the environment. I have a cell tower here, but this could mean any kind of sensory input, such as conversation or observation or sensation of the body. So this is a very general sense of a signal. They consult their knowledge of how that relates to some future event. They allocate their resources, and then the environment samples an event and returns some resources to them. And so this happens essentially on a cycle. And so you can show that with this kind of setup, you can compute the agent's average growth rate over long times and show that it's this information theoretic quantity, where this first term is the mutual information between the signal S and the event E that the agent is trying to predict, as well as some information divergence term between the agent's model of the environment and the true relationship between those signals in the event in reality. And so in this sense, this first term provides you a measurement of the optimal accuracy, or essentially the speed limit of your growth in your environment, given those signals, subtracted by however inaccurate your agent is. And so when I say growth rate, this is the same kind of growth rate that you find in geometric Brownian growth models, geometric Brownian motion models of wealth dynamics. And so this classic model is widely used across particularly econophysics, but generally in many different kinds of cases where you're trying to understand stochastically growing systems. And so in recent literature, this has been used to understand the capital growth rates, to understand the relative balance of optimal tax rates when you have public and private growth within a society, as well as understanding the convergence times of the US wealth distribution. I recommend you guys check out these papers. They're really great if you haven't. But this is generally a very popularly used model to studying wealth inequality. And the three primary variables used in this model are the resources, or a proxy for the agent's wealth. This quantity that in the case I just described, the agents are investing in their environment and receiving returns for. The volatility, which is essentially the average fluctuation that the agent experiences in their growth, and this growth rate gamma, which I just showed in the last slide. And so in these GBM models that are commonly used, they typically consider a homogeneous case. That is, every agent across the population has a uniform average growth rate. And so in the case of what I just described before, that means all agents essentially have the same information. Now, in this case, the variance of the resources in the population grows proportionally to the volatility. So the fluctuations in growth And so generally that means that volatility drives inequality, if you think of inequality as being a measurement of the variance of the distribution. So we can consider a slightly more realistic case where the growth rates and the resources are initially distributed across a population. So what I've done now is introduce the sigma r term to represent a variance in resources, and this sigma gamma term to represent a variance in growth rates. And we see now that the dynamics of the variance becomes much different. We have different quantities contributing to the inequality on different timescales, particularly on long timescales. We have this big contribution, this quadratic contribution from the variance in growth rates. And so we can demonstrate this effect using really simple measurement of Gini, a commonly used measure of inequality on geometric Brownian growers, where this dashed line shows the homogeneous Gini for a population evolved over 200 time steps versus a heterogeneous population. And we generally see that the heterogeneous groups, their inequality increases much more rapidly. So generally, heterogeneity is really bad for managing inequality. So the first benefit of this new theory is in really explaining where these variations in growth rates come from in terms of agent characteristics within their environment. So we can see this by looking at this equation here, the variance in the growth rates, and we see that there's three primary components. First is variance in information, which is really a variance in the agent's model. So what is the structure, how do they make decisions in their environments, but also how does the environment reward their decisions? So this first term is really something fundamental about their environment. The second term, this variance in the DKL, is a measure of the agent's divergence from that optimal. So not only how wrong are the agents, but how does that wrongness vary across the population. And then this third term is just some covariance that we can get some intuition for. For example, this covariance could be negative if younger agents might have better models but less experience. So their I is larger, but the variance in D is smaller. The DKL is smaller. Or we could think of a positive covariance case where agents that have better models simply learn faster. Also, I just want to stop quick to say, if I'm going too fast, please feel free to stop me, go back, ask questions, etc. So for the model that I'm about to show you, we're going to assume a shared environment across all agents. So
one second. There is a question from the.
Sorry for interrupting. So maybe I missed this part. How do agents update their distributions, the ones that they have in mind? Like, is there a Bayesian framework?
Yeah, we'll get there.
Okay, thank you.
We're just defining the growth component, but we'll explore that shortly.
Thank you.
Anything else?
No, thanks.
Okay.
I have another question for so. Is it that one? Yes. Okay. Can you hear me correctly from here?
Yes.
Okay, perfect. So the picture that I have so far, so let me know if I'm wrong, if I got it correctly, is that there's some distribution of events that the agents don't know about. Then events happen according to this distribution, but the agents have some, I guess, imperfect information taken from another distribution that more or less that I guess is somehow related to the distribution of events that actually happen, and the closest the internal distribution or the internal implementation of this distribution that the agents have to the distribution of events, the more they benefit from it. Is it more or less how it works, or did I?
Yeah, so the closer that, the more that S predicts E, so the more that their signals predict future events, the more information they'll have about events in the environment, and on average, the higher they'll be able to grow. As growth rate is a function of, or is the information in this case.
And what is the relationship between the distribution of events and the information?
So the way that we've described this theory really leaves that choice up to the modeler. So I will soon give an example of a particular model. But we've defined this in a way that this environment can really be anything. It can be some, hierarchical sequence of distributions that, the agent might receive a signal at some level of that sampling process and then try to predict some downstream event. It could be something really simple like just like two binary signals predicting an event. What this provides is really just a framework for an agent to interact with that environment and gather resources from it.
Okay. There are no more. Yes, no question.
Okay. So so I'll provide an example to illustrate what I mean. So let's take, for example, some farmers who, on an annual basis, they want to plant, not just plant crops, but receive some payment from it from some market. So every year, the farmers receive a ton of information from their environment. They read the Farmer's Almanac, so they get some idea of what the food prices will be. They read climate projections and weather forecasts. And all of these signals essentially inform in their internal model how much should they plant and how much should they expect to receive. And so following the reception and the processing of those signals, they're going to actually plant their crops and allocate the resources, if you will. And then at the end of the life cycle of their plants, they will take their crops to market and receive some return for the crops they've grown. And so this of course occurs in a cycle throughout their lives. And I've provided a really simple case here, but this really is written in a way to apply to many other types of allocation cycles. For example, as students, we allocate a lot of resources early in our lives to education with the expectation that later this will help us gather more resources over a long time from our environment, right? So we can sit down and discuss, how does this cycle really relate to different types of experiences. But generally, this type of framework is common in the biophysical sciences and is used to study how organisms essentially interact with their environments. So back to the theory. Again, this growth rate is computed from an information of some distribution of the environment. We can come up with a really simple description of an environment to help us illustrate this even further. And this is the model that I use in the paper that's linked at the bottom here. And so we're going to assume a really simple description of the environment where we have n discrete signals and n discrete events. And each signal matches to an event with some probability p along the diagonal. And then all off-diagonal events will be uniformly distributed, conditional on S, and they all sum up to be 1 minus p. So essentially, this is some binary choice model where the sort of correct binary choice is the diagonal term, and then the off-diagonal terms are collectively the wrong binary choice. And so when you set up an environment like this, you get a growth rate that has a really nice closed form, where this L measures how many choices there are in the environment. P is the true probability that any S predicts, or the diagonal S and E relate, and X is the agent's guess of that probability parameter. We can also compute this volatility, so this fluctuation in the growth rates as follow. And then we can simulate this using Monte Carlo simulations. And these best fit lines are calculated assuming that these parameters here are geometric Brownian motion parameters. And so we see that there's really nice agreement between this theory and geometric Brownian motion generally. So we can also just try to, plot what these growth rates and what these volatilities look like. And so this, on the x-axis here, we have the agent's preference parameter. So essentially, how much will they invest on that diagonal term? And then the y-axis here is the gamma, and this bottom plot is the volatility. And so we see that, just as Kelly predicted, when the choice parameter is equal to the true environmental probability, we have a peak in our growth rates. When the agents engage in totally hedging strategies, so they invest their resources uniformly across all signals. So for L equals 2, that means 50% of their resources in either option, they experience no volatility, which also makes sense. But the nice thing that emerges from this that we see already is that for this particular model, one growth rate can map to two different volatilities. So we see that we already get some notion of preferences that emerge simply from the description of the environment. And what I mean by this, by preferences, is that you have a low volatility allocation strategy. So the agent will experience lower fluctuations. You can imagine that as a conservative gambler. And in this other case that has the same growth rate, they experience much higher volatility, so much higher resource fluctuations. So we've described a paradigm, if you will, for studying stochastic growth. We've demonstrated that inequality is driven by heterogeneity in agents' agents' information, and we've shown that heterogeneity really damages inequality or worsens inequality. So how do we manage inequality in these shared environments? So we're going to introduce a learning scheme where agents can now update essentially their information on the environment through some Bayesian inference process. And so essentially, as the agents observe combinations of signals and events, they are going to update that probability. And assuming that the environment is stationary over long times, which we've assumed in this work, but generally isn't true, the agents will converge to the optimal allocation strategy given their environment. And so what this means in terms of the agent's choice parameter, their x, is that their x will converge where this lambda is some measurement of time. It starts at x naught, which is their initial preference, or sorry, their initial choice parameter, and over long times converges to p, which is the environmental optimal. And so we can see this in this plot here, where for a population of learners, we can measure the difference between that x and the environmental p, and we see that it converges. The agents generally converge as this quantity predicts. So taking this back to this discussion about varying growth rates, what does this mean? If we compute the variance in these choice parameters across the population, we see that over time it converges to 0. So what this is really doing is erasing that heterogeneity in choices across the population. On average, I should say average choices, because on an intertemporal basis, every agent's making a decision that's based on the signals they receive. But we see that this variance goes to 0. And when that variance in choices goes to 0, we can see that we can approximate that the variance in growth rate does as well. And so this plot here is showing on some log axis that over time, this variance in choice parameter goes to 0 with power law 2 that we predicted in the equation on the previous page, and just showing like what that approximation of the growth rates look like. Okay, so what does this mean for inequality? So on this right plot here, I'm showing you now a comparison between 3 different cases of agent simulation using Monte Carlo simulations. So the idea is we have a population of n agents. Let's evolve them and measure how does the Gini and the coefficient of variation, which measures relatively how quickly does the mean and the variance of the distribution grow. So how are we growing versus how quickly is inequality spreading? And so in the first case, the homogeneous case, so all agents have the same growth rate, we see that there's a steady increase in resources across the population, and this shaded region, which is the 95% confidence interval of the resources, steadily increases. And so we see, some steady increase in the Gini here, and some leveling off of the coefficient of variation. When we introduce heterogeneous agents, we see that now the variance increases much more rapidly. Correspondingly, the Gini increases to 1 super quickly. The CV increases as well. But when we introduce learning, now, of course, the growth rate is going to increase as the agents converge to the optimal. But more importantly, we see that the variance, the width of that distribution stops increasing so quickly. We see that the Gini, although it starts at a really high value, it increases at a rate much more comparable to the homogeneous case, and the coefficient of variation decreases back to something more comparable to the homogeneous case as well. So what we've done here generally is introduce a new source of inequality through a heterogeneity in agents' choices, and fundamentally the information about their environment, and then shown how learning can be a mechanism. It's not always, but can be a mechanism for reducing that inequality. Okay, so for the second part of this talk, we'll now discuss how information theory unlocks new mechanisms for studying cooperative and collective behavior. And so what we'll do is now imagine, instead of just one signal, an environment with only one signal, imagine this environment has, tons and tons of signals that agents might have access to different ones. In this really simple case to illustrate, we'll just picture that there are 2 signals in the environment, S1 and S2. And so the question is, when agents collectively make decisions based off of those signals, how does the information, how can we relate the information of that decision to the information of just the individual decisions? So the typical way of computing how information aggregates is through this recursive strategy, where you calculate the information of the first variable plus the second condition on the first. And so what that looks like using some Venn diagram is that this overlap between these 2 distributions of E and S is now, we now add to that this region that is careful to not overcount that overlap, or double count that overlap. So we can do this calculation in a slightly different way, where we essentially add up all of the information of the signals separately, and then subtract away that overlap at the end. And so we can think about this overlap as being some quantity of redundancy across the signals, but this coefficient of redundancy can also be negative. And so when it's negative, what this means now is that there's really a superlinear benefit to pool, as we call pooling information. And so you can compute that redundancy term, doing a calculation here, but we're going to forget that for now. But what that really means, so first of all, we call this R. When R is negative, we say that there is synergy present in the environment. And so when there is synergy present, that means that collective decisions are really better than the sum of, the sum of individual decisions. So we can say definitely that there's a benefit of pooling information to make a collective decision. And so what we're going to do for the rest of this talk is think about what happens now when agents, as collectives, make decisions and pool their information. So we're now thinking of mutual information between the event and a collection of signals, as well as the DKL between some distribution of many signals and agents, or collective agents model of those many signals. And the general task for these agents now is to not just learn their signals, but also learn the synergy and how their signals complement one another. So what this really does in terms of enhancing the existing modeling scheme is it introduces a new dimension for these geometric in terms of these geometric Brownian growth models for cooperation. So typically what you see in the literature, whether it be through some taxation policy, through some resource pooling, which has a role as to redistribute wealth throughout a population. It also plays this role of sheltering from, or really averaging over the volatility. So what I kind of skipped over earlier is that this gamma and the sigma are related, where as your environment becomes more unpredictable and more volatile, the lower your growth rate will actually be on average, where this eta measures the average returns that an agent receives. So hedging by pooling resources starts to mitigate this volatility, while synergy in some ways directly can increase the growth rate across your population. So we now have two not quite orthogonal, but close to orthogonal methods for agents to benefit through different modes of cooperation. So now I'm going to demonstrate a particular environment that actually has synergy. So if we continue in this vein of using really simple binary choice models to illustrate these principles, logic gates give us a really nice way of extending these environments to higher dimensional signals. So particularly consider the XOR gate, where if you think of each agent as being each agent as being an input, receiving that input as a signal, we would consider this XOR gate to be maximally synergistic. And what I mean by that is for agent A, if they receive a 0, the output is totally random. It could be a 0 or 1 with uniform probability. If the agent receives 1, it's still uniform. However, when you have both signals present, so if agent A asks agent B, hey, what signal did you get? They can always predict what the outcome will be. So in this sense, the agents alone have no information, but combined, they have complete information about the behavior of this logic gate, if their goal is to predict the output. Now, for this environment, we're going to mix this up a little bit by saying now, instead of just the output being some deterministic quantity, it's now a 0 or a 1 with some probability p, where that p is unique to each combination of inputs. So for 0, 0, there's some p1 that describes the behavior of the gate. For 1, 0, there's p2, et cetera. And so this equation is missing an equal sign, but the distribution of the environment in this case looks like this quantity here. And so we can ask now, for environments of different sizes, so for environments of different numbers of signals, and for groups of signals of various sizes within those environments, how does the information scale? And this is what that looks like within this environment. So what we see here, each color represents an environment of a different size, of a different number of signals. So when L equals 2, that means there's 2 signals in the environment, and up to 12. And so this x-axis, what we call the cooperance, is the number of cooperating signals that are trying to predict that event. And we see that for generally, noting that this y-axis is on a log scale, generally that as we increase the number of cooperators, the information they have access to scales exponentially. So we're not, of course, trying to argue that this is how true environments actually work. This is just a toy model to demonstrate these principles of synergy. And so what this means is as a group of agents collectively make decisions with more and more signals, they're going to have more and more information and grow resources more quickly. So do we have any questions so far about that? Great. So to demonstrate this using simulations, we're going to assign agents randomly a signal. So for example, this agent will get signal 1, this agent gets signal 5, and so on. And then we're also going to assign each agent randomly to a group. So we'll call this group 7. It has 6 members. We have group 15 with 1 guy in it. We have group 3 with 3 people. We're just generally randomly assigning people signals and randomly assigning them groups. So for this simulation particularly, we're going to say that there are 4 signals in the environment, and group sizes can get up to 11 agents. And so now we can ask, okay, as these agents are growing, as they're learning, how does their information evolve? How do their resources evolve over time? And so we see in these two plots, we'll start with the top plot, first looking at the legend to see that the color indicates how many unique signals are present in a collective. Looking at this top plot, we see that over time, each of these groups of different signal sizes gather information differently. So for groups with low number of signals, they really cap out at a low level of information, whereas groups with a high, as we increase the number of signals in the group, the more they learn, where the groups with the complete amount of signals learn easily the most information from their environment. And then when we then look at how many resources do they accumulate over time, we see that, as we expect, the groups with more information accumulate more resources. And so we see, generally this simulation and this setup really works. So you might be wondering, why do these groups with 3 signals or 2 signals, why is there such high variance in both the information they acquire as well as the resources they collect? And that's because within each of these signal sets, there could be many different combinations of signals that result in that number. So for example, as we show on this plot here on the left, we can look at groups of size 2, so 2 unique signals, and of size 3. And we can see, of course, first that there's different combinations. So with 2 cooperants, you can have 0, 1, 1, 3, 1, 2. And what that means specifically is that this group is using signals 0 and 1, or 1 and 3 to make a decision. Second, we need to convince ourselves that this is actually some kind of synergy interaction going on, and not just agents, adding their information together. And so we're comparing with the little dot, how much information do they have if they simply sum or average their information, and the bigger dot on the right is what happens when they actually pool their information. And so we see that pooling, clearly increases the amount of information they have access to. Now, third, and this is really the most important part of, or the most important insight of this work, is that it's really hard to predict which combinations of signals result in more information. So for example, while combination 1, 2 has more information than combination 0, 1, when averaged, when pooled, 0, 1 has much higher information. For example, and another example is, it's not straightforward to see why does signal 0, 1, 3 in a combination do so much better than signal 0, 2, 3. And so what we're really highlighting here is the challenge towards intelligently assembling a set of signals given some description of the environment. And so this problem of, one, how do you recognize the complexity in your environment? How do you form a group so that you can not just match that complexity, but do so efficiently and make quick decisions, is generally an open problem in the managerial sciences literature, and really just the challenge of being a manager in any capacity. So what we introduce here is a principled way of thinking about how skills complementarity can be computed in terms of information. So we call this principle the principle of maximum synergy. And what it really states is that simply the most successful groups will collect and assemble their signals in a way that maximizes the synergy in their environment. And so one more challenge of satisfying this principle of maximum synergy is, once you've assembled your group, as we show in these plots here, it takes quite a bit of time, in some cases, 50 or 100 steps to really resolve the synergy that you have present. And so it's difficult to know a priori, whether a collection of signals that you have is synergistic. So it generally group formation, as we see here, is a time-intensive and costly process. And so what the direction in which this research is moving is really trying to understand how does social interactions, how does it differ across scales of organization, or as ecologists would say, levels of selection. And furthermore, how do different collective strategies vary? So for example, as the agent collects into a family or community, we might expect that resource sharing becomes more of a dominant strategy than information sharing, whereas as a heterogeneous population emerges, there could be potentially information sharing. And the intuition for why these different strategies emerges comes from what that strategy is aimed at doing, right? So we don't have kids with the expectation that they will give us new insights while they're young. It's more that they rely on us as a way to shield them from the volatility of the world. Similarly, when we, assemble groups, working groups of people with complementary skills, we're not expecting that we all share our wealth together. We're more expecting that the complementary information that we share will lead to better decisions, better progress, etc. But depending on how your group assembles and what purpose it serves, there could also be separate strategies. So for example, a firm might rely more on novel decision making, whereas a government might rely more on better resource management. So we see, as we go up this chain of hierarchy, we see more and more mixed and complex strategies. So what we're working on now is trying to understand what this phase diagram, if one exists, what it might look like in terms of the volatility in the environment and the information complementarity across signals. We expect, as we move our environment through this phase space, different cooperation strategies might emerge, where in a low volatile, high information complementary environment, sorry, this x-axis is volatility correlation, which means, so as hedging really only works when signals are when fluctuations are uncorrelated. So as we go towards zero on this axis, that means that there's more independent volatility, and that resource pooling is a better strategy. So in this top left axis, we might get something like cities or conglomerates, where you have both a combination of synergy as people are introducing new ideas, but also shielding from volatility within their environment. Whereas in this bottom left quadrant, where there's low information complementarity but low volatility correlation, you might get something like a state where your primary goal is just to shield from uncertainty or to pool resources. So that's one project we're working on. But generally, this framework applies to a lot of different active research fields. So for example, in ecology, people are trying to understand generally like inclusive fitness. So what are the benefits of cooperating with people who are similar but also might be different from you? Where in the 80s, they started to really appreciate that there are higher order benefits to cooperation when agents coordinate their actions. So what this work does is it really formalizes that higher order term in terms of the information in the environment, which will lead to a better understanding of decisions over complex and heterogeneous networks, where each agent could be making different decisions using different signals, but where their wealth and their signals are related. So just generally building towards a more integrated models of social network inequality. We're also interested in applying this research towards psychology or an organizational research. So really understanding how do complex organizations emerge from agents with complementary skill sets, and economics. Of course, game theory is a huge active research field. Well, what I've described here really gives us a way of defining game rules by simply averaging over and marginalizing out the stochasticity of the environment. So when you do that, now you essentially have a a matrix, much like a reward matrix that tells you, how much do each decisions by an agent, how does that reward them? But with the added benefit of now we can think about these benefits and costs in terms of synergy. And then lastly, we're also interested in studying more competitive social dynamics, such as principal agent problem or models of markets, where thinking particularly about this Bayesian mechanism as a way for agents to adjust their preferences or their desired prices for an asset, we can use this framework to study how do agents adjust their preferences as they observe each other's behaviors, as they observe reality checks from their environment, etc. So with that, thank you very much. This work is supported by a lot of different people from a lot of different places. And this is me and my advisor, Luis Betancourt. So with that, of questions, please. Thank you.